because I see many people are still connecting.
Yep.
All right, are you ready, Valerie?
Yep, good to go.
Okay, so we're going to start the recording, okay? All right, so we are very happy to have Valerie Domke, who will start the set of lectures on gravitational waves from the early universe.
Yeah, thanks a lot. It's really a pleasure to give these lectures. In a way, I've been looking forward to this since I was a master's student myself, visiting the ICTP summer school. So yeah, the topic of today is gravitational waves from the early universe, and I invite you. Some of you have already figured out what's with the QR code here. So I invite you to either scan the QR code or just enter the address of this link here. This is to have a little bit of interaction during the lecture. So the first question that you'll find when you click this link is a question kind of about how much you already know about gravitational waves, which will help me to judge the correct level for the lectures. So the outline for the 3 lectures that we now have in the next 3 days is today we'll cover really gravitational wave basics. Many of you will have heard something about gravitational waves, but I do want to spend some time explaining what a gravitational wave actually is. Because it's not quite as trivial as one might think. Then tomorrow we'll talk about the stochastic gravitational wave background. That's essentially the gravitational analogon of the cosmic microwave background. And then in the 3rd lecture on Friday, we'll see kind of how we can use the stochastic background to actually probe particle physics with very high energies. So here's some literature relevant for the course, in particular these first. I mean, essentially this first item is more or less the first lecture, and then the second 2 items will become relevant for the other 2 lectures. And just to give you a feeling, so you can see how much maybe the other people here in this room currently know about gravitational waves. This is the current status of the polling results. So I see we have a couple of experts. But it seems I'll be able to teach all of you something, I think. Okay, so let's get started. So the first topic that we want to talk about is the wave equation, which is essentially the defining equation of gravitational waves. And to do so, we will start from Einstein's equation. And I'll be doing essentially all of the lectures I'll be doing in handwriting. So I mean, you know best what's the best way for you to learn, but I do encourage you to take notes if you find that useful to follow, because I won't be writing down absolutely everything that I say. So Einstein equation relates on the left-hand side objects that are related to the metric. To on the right-hand side, object related to the energy content of the universe. So G here is Newton's constant, C is the speed of light. At some point I'll switch to natural units, but let's keep them for the moment. And this entire left-hand side is also often called capital G mu nu. And so what essentially Einstein equation tells us is that the curvature of space-time here on the left which is described by a metric tensor g mu nu, from which, as you can see, once we have g mu nu, you can essentially compute this entire left-hand side. So this contains essentially the geometry of GR. This is influenced on the right-hand side by the energy momentum tensor of the matter content of the universe. So this T mu nu is the energy momentum tensor. And essentially what GR tells us is that the way space is curved influence how particles move in space, but also the energy content of the universe itself can curve the metric. So this is really an arrow going in both directions. And now what we want to study when we study gravitational waves, we want to consider a small departure from flat space-time. So consider small departure from flat space-time. And then we want to compute essentially, this is really what we do the next 5 minutes or so. We want to compute what this left-hand side of this equation is. So concretely, we want to express this general metric as some flat metric, which I will call eta mu nu, where I'll be using the mostly plus signature, so this signature. And then I'm going to perturb this by something which actually depends on space and time, with the condition that this perturbation is supposed to be small. So this is essentially the validity of the analysis that we'll be doing throughout these entire lectures. And the convention will also be that whenever I raise or I lower indices, I will always do this with this flat metric component here. So now once you have an expression for the metric, you can plug essentially this into the left-hand side, and you can compute what is this capital G mu nu object. And then the goal is essentially to find an equation which tells us how this perturbation of the metric, which at the end of the day will be the gravitational wave, how that kind of evolves, depending also on the energy content of the universe. So here now comes the point where I can cheat, because this is not a real Blackboard lecture. So this is just showing you, if you've had a GR lecture, you'll have seen this. If you haven't had a GR lecture, you'll just have to kind of believe me. But this is essentially how you, starting from a metric, you compute the left-hand side of this object. And really, it's all just a big contraction of indices. So not particularly insightful, but let's just have a brief look at it anyway. So the so-called Christoffel symbols are essentially what, this described essentially sometimes the connections of GR. So the Christoffel symbols are this is the definition, right? Is the function of the metric tensor. Now we insert the linearization of the metric tensor. So we replace with this equation here with the constant part plus the perturbation. And now we expand to first order in h mu nu. And then at linear order, we get this term here, right? 1 power in h. And then we have higher order corrections, which we will drop. Then once we have the Christoffel symbols, we can compute the Riemann curvature tensor, which we can derive. Again, this first line is the definition, as soon as we have the Christoffel symbols by taking, again, contractions and derivatives. And in particular, this second part of the curvature tensor always involves two Christoffel symbols. But since every term in the Christoffel symbol is already proportional to the perturbation h, it means that if we contract two of them, it will always be of order h squared. So since we will always only here want to do the leading order expansion, we can immediately drop these terms. So we can then plug this expression for the Christoffel symbol into here, this expression for the Riemann curvature tensor, do all these derivatives and contractions, we end up with this expression here. But in particular, we have some terms here which are symmetric in some of the indices. So for example, this term here, right, is a d alpha, d beta. So of course I can commute the derivative. So this is the same as d beta, d alpha. And then I have these three terms, and I have then again the same terms where I switch alpha and beta, which means because of the minus sign here, means all the terms that are symmetric and alpha and beta will cancel. So this term will essentially disappear at the end of the day. Oops, to go back to being a pencil here. So we will have this term, and then the same 2 terms again, where we've switched alpha and beta. So 4 terms in total. And now we can, by a simple contraction, we can get from this Riemann curvature tensor, we can get the Ricci tensor, R menu, which is already one of the objects inside here. And then if we perform another contraction, we can get the Ricci scalar, which is the other object that was inside here. So this is this kind of blows up quite significantly. In Majora's textbook, you can find a full computation. But if you manage to do it correctly and not lose any minus sign, then after quite a bit of work, you arrive at the final expression for G mu nu, which is a minus 1/2 box H mu nu plus eta mu nu. So the box is just 2 partial derivatives, del rho, del sigma, H bar, rho sigma, minus del rho, del mu, H bar, mu, rho, minus del rho, del mu, H bar, mu, rho. So now you see why I took this shortcut beforehand, because with all this indices writing, I'm bound to make some mistakes. And here I've introduced this object H bar, which is I defined as I introduced it simply because it makes the expression more compact, and it is given by the original H mu nu, so our perturbation, minus 1/2 eta mu nu H, where H is the contracted version. So this is H alpha alpha. So I essentially subtract the trace, and this makes my expression more compact. So this is the final result for the left-hand side of the Einstein equation to first order in perturbation theory, right? So then there are correction terms which are order h squared. And this is an important equation, so I'll give it a star so that we can refer to it later. Maybe are there any questions on this very first part? So I repeat that kind of the goal here is to derive an equation of motion for this metric perturbation, which at the end of the day will be the gravitational waves. And then that will kind of tell us how gravitational waves are related here by Einstein equation to the energy density in the universe. And that then at the very end of the day, meaning on Friday, will show us kind of how we can use gravitational waves to probe actually particle physics, because all the particle physics is in the right-hand side of this equation. Okay, so now we need to understand a bit better what is this object H mu nu, which is appearing here to first order in perturbation theory. And so for that, I have another poll for you. So you should now, if you still have it open, the poll thingy, you should see a new question. Otherwise, you can enter again this link here. So this is just, don't think about it for too long, right? So this is just to give me also a bit of a feeling kind of where you stand. So the question that I would like you to answer now is, what are the symmetries of the linearized version of GR that we're just in the process of derising, right? We linearized means that we kicked away all the order h squared and whatnot. Maybe I should do this blind, right? I should not let you see. Now everybody's just clicking what everybody else is clicking. Yeah, so there's a question in the chat, where does one see the poll? So I don't think you can see the results. I think you can just see the questions, and the questions you can see when you go to this link here. Then you should be able to see the questions and participate. Right, so there's a big majority for infinitesimal coordinate transformation and global Poincare transformation. And that is correct, which is kind of interesting, because general GR has this first symmetry, right? So this is the symmetry of all coordinate transformations. Somehow when we linearize it, we lose part of the symmetry. And the reason we lose it is the following. So let's talk about symmetries. So we start in full GR, we start with the general coordinate transformations. But then this actually breaks down because we do this linearization. So we divide this. We said we divided this g mu nu, right? We say we divide it in some eta mu nu plus h mu nu, right? Which means we somehow define a constant background and then fluctuations on top of that background. But to define a constant background, you need to do an averaging process. And to do an averaging process, you kind of need to define over which time slice you are doing the averaging process, right? So in some sense, you are doing a time slicing and then you're averaging on each time slice. And hence you no longer have the full symmetry, but you only, due to this first step, which is associated to the background, you only have remaining the SO3 symmetry of global spatial rotations. And this is precisely where we lose the bigger symmetry of GR is precisely because we do this linearization process. So now that we have global spatial rotations, we can use the fact that we only are interested in the linearized theory, which means we can do a Fourier transform and all the K modes of the Fourier transform will behave independently. And hence this Fourier transformation, we can kind of single out an individual K mode and we can study only that K mode. So the second step is essentially to do a Fourier transformation, which singles out one particular direction K that one can then study. And then with respect to this particular direction K, one then has an SO2 symmetry, which describes the helicity eigenstates with respect to this vector. So essentially you have some object, like X, for example, right? And then you perform some rotation by some angle theta around this vector K that we've selected. And this object here will pick up a phase, e to the I m theta X. And now depending on what this M is, this essentially classifies these objects X. So if M equals 0, so essentially if you do this rotation and the thing does not rotate, then the thing that you were looking at is a scalar. If M equal 1 or plus minus 1, it is a vector. And if M equal plus minus 2, it is a tensor. So to say is that we started with a full symmetry, then we can realize that actually in our linearized theory, this actually breaks down to a reduced symmetry, but within this reduced symmetry, we can classify our perturbations by essentially a quantum number, which is essentially the helicity on the rotations around the vector, which is specified by the Fourier transformation. So let's do this concretely, because what we're actually interested in is, say, this G mu nu object, right, or the H mu nu object, one of both. So for G mu nu. So G mu nu, we can write as G00, G0I, Gi0, Gij, right, where Ij run over from all spatial indices from 1 to 3. And now, if we do this step 1 here, and we do this in a very physicist way, where more formal people will be horrified, the way of doing this is essentially drawing lines here and saying, I distinguish between temporal indices and spatial indices. And then to do the step 2, so to actually define these perturbations, what I need to do is essentially write down all possible perturbations that give the correct index contraction. So let me do the example, and then I think it will become before I do that, I have a question for you. So the question is in the poll again, and the question is how many independent degrees of freedom do you think are inside this metric tensor? Okay, I'll continue and then we'll see the result at the end. So we look at the G00 component, then if we just have flat metric, then this is just -1. And now I want to add a fluctuation to that, but I have to add a linear fluctuation such that it has no spatial indices, because as soon as spatial indices, the spatial indices on the left-hand side and the right-hand side have to match, and the left-hand side does not have any spatial indices. So all I can do is essentially add one scalar perturbation, right? Scalar means no indices, which means it rotates with this, changes with this m equals 0 with the scalar under these helicity rotations. Now, we can do the same for a spatial component. So here we can get, from here we got essentially one scalar. So we do this with this mixed component here. So this is the same because this is symmetric, the same as this, right? So there's a if we just had the flat space-time, this would be 0, right? The metric tensor is diagonal, so there's no leading order term, there's only perturbations. And now we need something which gives me one spatial indices, right? So the one way I can do it is by taking one spatial derivative of a scalar, or by taking a vector directly. So B is now a scalar, SI is a vector. Vector meaning it has kind of no, the divergence should be 0, so that there's no scalar component inside. So this gives one scalar, this is this B, and one vector, this is this SI. And then we can do the same game with the pure spatial components. So now the flat space papa would just be 1. Now we need to add something which is 2 indices, right? So one way of doing it is by adding a delta function. Another way of doing it is by adding 2 derivatives. And another way is by adding one derivative and one vector. So for example, like this, Tj, again, we have to make it symmetric. Or we can add an object which is already by itself a tensor perturbation. So here we have now 2 scalars. This is the psi here and the f. We have one vector. This is the capital Ti here. And we have one tensor. This is this Tij. And now we can count all of this together. So we have 4 scalars in total. Then we have 2 vectors, but each vector has 2 degrees of freedom. And then we have one tensor. The tensor also has 2 degrees of freedom. So in total, we have 10 degrees of freedom, as one might have anticipated from a symmetric 4x4 tensor, right? Because if I have a symmetric 4x4 tensor, you can kind of count how many entries can you have just by doing this trick here. So 1, 2, 3, 4. Right now you count the dots and it should be 10 because the downstairs components here are already specified from the fact that it is symmetric. So the answer that essentially the majority vote here is correct, right? So we have 10 degrees of freedom in the metric tensor to start with. Okay, but now, okay, and then why am I going on about this? I'm going on about this because in the end, we want to study gravitational waves, which will be one of the perturbations inside this metric tensor. But preferably, I would not like to deal with 10 degrees of freedom simultaneously, but I would like to reduce this to a system which is fewer degrees of freedom and I actually understand better what I'm doing. Any questions so far?
Yep, there's a question by Mehmet. Please go ahead.
Hello. So when you classified the types of representations that we just counted, you used the SO2 group. And probably it will be tied to the fact that we have a massless particle, but you never told it explicitly, right?
Correct. Yeah. We have right. I'm already anticipating that there's no mass term here. Correct.
Not a very concrete question, but just out of curiosity, if you had a massive gravity, or I don't know, if you didn't have this masslessness, then this classification would break down or modified?
No, so the classification works as long as you work in linear order in the perturbation theory, because this is really a very, very general kind of way of classifying cosmological perturbation. So this does also work when you have a mass. What happens when you have a mass is that, however, the degrees of freedom, as not the total degrees of freedom, right? Total degrees of freedom are fixed. But for example, if the graviton, right, had a mass, then it would have more. Well, we will come to that later, right? But it have potentially more degrees of freedom.
I see. Okay, thank you.
Yeah, to briefly answer to the chat, this is TJ-TI, so del I TJ, del J TI. And yes, all 10 degrees of freedom are independent. Yeah, this is what creates the mess, right? Because if we have to actually treat 10 degrees of freedom, this is a quite complicated system. But the goal will be to reduce this.
Right.
Okay. So we can now use gauge invariance. Or yeah, we can use it, and in particular, we have to be aware of it. And with gauge invariance, what I mean is the invariance under coordinate transformations. The reason being that at the end of the day, if I perform a coordinate transformation, the physics may look different in a new system, but actually the physics that I'm describing has to be the same. So consider an infinitesimal coordinate transformation. And I have the feeling this will answer some of the questions in the chat. So we take some spatial vector x mu, right? We shift this by some constant epsilon mu. And the physics has to be invariant under the shift, the total physics, right, in the full theory. And this epsilon mu, we can now do the same trick as we did above. And we can write this as a spatial component, which should be a scalar, and a spatial component, which can contain a scalar and can contain a vector. This is the most, but again, we have this condition that del I fi equals 0, which tells us that in this coordinate transformation, we have contained inside two scalars and one vector, which means that essentially we have two scalars and one vector in the system which are not physical, right? But we can essentially go to different bases, and then they will appear to be gone, so they will be gauged away. And hence, we can impose a gauge condition, which will make our life a lot easier. We can essentially force these degrees of freedom to disappear, and we can impose precisely Lorentz gauge. And as an anecdote, note that the spelling here is actually, this is named after the wrong Lorentz, actually. It was the other Lorentz that first did the Lorentz gauge, but this is kind of the way it is now established in the literature. So we can impose Lorentz gauge, very similar to electromagnetism. And this is a gauge fixing on essentially the scalar and the vector sector, right? We're not touching the tensor sector. In fact, we can see from here that the tensor sector, so the Tij up here, is gauge invariant, because this coordinate transformation did not include any tensor degrees of freedom. But imposing this condition, we can now go back to the expression that we computed for G mu nu, right? And you can see that kind of we have lots of terms where the derivative are acting on the h mu. And the only term that is left once we do this is that box h bar mu nu is the only thing that is left on the left-hand side. And then on the right-hand side, we have, as before, 16 pi g C4 T mu nu. So this is now our result for the linearized Einstein equation. Oops. Okay, we have a very simple equation where on the left-hand side we're acting with the box operator, right? So this is nothing else. This is del alpha. We're acting on our perturbation h mu nu. And then on the right-hand side we have the energy momentum tensor. Question for you: now that we have imposed Lorentz gauge, how many degrees of freedom do we have left? So you can again check in the polling system. So what this equation do, so this equation is a very powerful equation. It describes both the sourcing of gravitational waves, so the right-hand side sources the gravitational waves which would be on the left-hand side, and it also describes, if we set the right-hand side to 0, it describes the propagation of gravitational waves. Yeah, and again, the majority vote wins. So we had 10 degrees of freedom beforehand. This condition here, this is 4 equations, Lorentz gauge, right? Where new index is free, so it's 4 equations. So at this point, we are left with 10 minus 6 is 4 degrees of freedom. We can now do one more step to simplify the system, and that is that but this step we cannot. Well, we can always do this step, but this step can be more or less complicated depending on the environment. So now let us just consider the situation in vacuum. So in vacuum, we have T mu nu equals 0, and this means
there's a question from Ivan. Probably it's from before. No?
Hello, can you hear me?
Yeah.
Could you repeat how many degrees of freedom do we have left after fixing the gauge?
Here, 4.
I don't understand why.
So we had 10 beforehand, right?
Yes.
And this here are 4. Wait.
I thought 10 minus 4 equals 6.
Yeah. Sorry, this is what I wanted to write. Okay, yeah, no, yeah, sorry. Yeah, exactly. This is also why everybody was correct, right? Yes.
May I ask another question?
Yeah, and thanks for pointing this out. Yeah.
What are GUs?
Gravitational waves. This is a W.
Okay, thank you.
Yeah. Thanks. Yeah, multitasking is complicated for lecturing. Okay, so in vacuum, the energy momentum tensor is 0. And in that case, we have a residual freedom, because essentially if we have, we can, in any epsilon, which satisfies that box epsilon is 0, right? In any epsilon that satisfies this, we can always add, or maybe we should call this epsilon prime, right? We could always add this to our transformation above, and it would not change anything here about the Lorentz gauge, but kind of it still gives us residual freedom to manipulate our h mu nu tensor. This is exactly the same as the way it works in electromagnetism. So residual gauge freedom, where I recall that with gauging here, I'm always referring to these coordinate transformations of general relativity, right? There's no whatever abelian, non-abelian groups, any of that, right? No U1, SU2, such. It's really just the GGR symmetry that we're talking about. And to fix this residual gauge freedom, we can, in vacuum, we can use a very simple prescription. And that is, this prescription is called the transverse traceless gauge. And the prescription is that we set the trace to 0. So H alpha alpha, if you want, is 0. And we also set the mixed components, so the 0i components, to 0. So you can see this is again now 4 equations, right? This is 1 equation, this is 3 equations. And at the end of the day, if you add this condition and the Lorentz condition, then you can always impose or you results in the following conditions. So in this transverse traceless gauge, as soon as you have one time-like index, the thing is 0, and also the trace is 0. In particular, the trace over the remaining spatial degrees is 0. And of course, we still have Lorentz gauge. So this TT is for this transverse traceless gauge. And these are the final conditions for the what is called the TT gauging. And so now, one more time, right? The question is, how many degrees of freedom do we have left? You can again, one last time, I will ask you for your favorite number here. Yeah, so the majority vote, yeah, very good. The majority vote is looking very good. So exactly, so we have 2 degrees of freedom left because we had 6 here at the end of the previous step. And then this here are 4 equations, or also here, this thing essentially are 4 equations. And so we have 2 equations left at the end of the day. And the object that we have left, if we go back to the very beginning, the object that we have left, the only object which satisfies all these conditions is in fact this pure tensor object that we had at the very beginning. So what this tells us that in that kind of the only propagating now, and this is now it's important that gravity is massless, right? So the only propagating independent degrees of freedom that we have in the metric tensor here are really the 2 gravitational wave degrees of freedom, and these 2 degrees of freedom is essentially the ones we want to study, and we want to understand their dynamics. And for this, it will be essentially this linearized Einstein equation is the key equation governing the dynamics of these degrees of freedom. So this is, to emphasize, this is really a pure prediction of general relativity, right? It's a pure classical theory. We don't need to quantize anything or talk about quantum gravity or anything like that. So we have a pure prediction just from the Einstein equation. We can derive an equation of motion, which we will study in the second part of the lecture, which kind of tells us how these 2 degrees of freedom that we have left with it at the end, how they can propagate and interact with the universe. Okay, this is a good time to take a break, and also happy to take any more questions.
Sounds good. Should we take maybe the break first, and then when we come back, maybe we'll have more questions after thinking for 5 minutes?
Yeah, perfect.
Okay, so see you in 5 minutes. All right. Are you ready to continue?
Yeah, yeah.
So, are there any questions before we resume? Seems there are no questions.
Yes, I
there's
see
a question.
one. I see one.
Yeah, by Maria. Please go ahead, Maria.
Hi, Valerie. Thank you for the lecture. I wanted to ask you about this sequence of steps that you were describing to talk about the symmetries. Could you briefly maybe explain the second step? I didn't get it right.
Yeah, okay. So right. So in some sense, yeah. So this, yeah. So okay. So from the first step to the second step, right? We realize that once we go to the linearized theory, we do this time slicing, and hence instead of we only have kind of the spatial symmetry and no longer the full space-time symmetry. Now the next observation is that since we are only interested in doing a linearized theory, so the object we want to describe is our h mu nu, and we have restricted ourselves to the regime where the h mu nu is small compared to the background metric. So we're going to drop all terms which are h squared or higher. And hence, since we're working in a linearized theory, we can do a Fourier decomposition, and then there'll be a big d3k outside of kind of every term, and we can remove this d3k everywhere, and essentially only study like the equation for every individual k mode will look the same, and in particular two different k modes, two different momentum modes will not interact. So we can study the equation of motion for one particular momentum mode, one plane wave solution, and we don't need to know anything about the other plane wave solutions. There will be no interaction terms. And hence, I can just specify one particular direction k. So k here is the momentum mode. And then kind of study, this gives me a preferred direction, and then I can kind of study the physics, which now has this preferred direction. And now I can essentially look at helicity states with respect to this particular k mode. And these helicity states now essentially tell me that in some sense what these helicity, so here I also did not give you very many details, right? But these helicity states, which essentially these tell you like if I do a spatial transformation, right? So say I do an SO, or I do this SO2 rotation, and then some objects essentially will transform under this SO2 rotation, and other objects will not transform. And essentially how these objects transform, which is encoded in this M here, is essentially identical to the way we associate spatial indices with them. There's of course a much more formal way of doing this, right? I mean, a mathematician will be absolutely horrified by this description of it. So the more formal way of doing it is, of course, to checking kind of, okay, looking at the representations under this first symmetry, seeing how they break down into representations of the second symmetry, and then checking how this kind of breaks down into representations of this third symmetry. And then you will find exactly these different classes.
Oh, okay, thank you.
Any more questions? Okay, so now let's study the properties of gravitational waves. And before we study them, I'd like to kind of know how much you maybe already know about them. So there's another question in the chat to see. But you probably cannot answer it from kind of what I've told you so far, right? But maybe you know anyway. So we now want to talk. So I should maybe put this here just in case. So this is, oh, now I lost it. So this is in case anybody wants to participate who doesn't have the link yet, right? So here, this is the link you need to enter in order to participate in the polls. So we now want to study plane wave solutions in an analogy to electromagnetism. I should put this in quotation marks. So we're looking at solutions to this equation here and trying to understand their properties. And we want to do this in vacuum. So we want to set T mu nu equals 0. So we'll be studying essentially the propagation of free gravitational waves. So we can start by making an ansatz, because actually this equation here, this in particular, if you set the right hand side to 0, this should look pretty familiar, right? Box something equals 0. This is just a usual wave equation. So we can solve it with the usual ansatz for wave equations, just that we have a couple of indices more. So h mu nu of x, you can make an ansatz that this should be solved by some amplitude which can depend on k, right? So this is essentially a plane wave solution of Fourier transform, and then sine k alpha x alpha. Then we can check. So we plug this ansatz into our equation, box h mu nu. So then the derivative here acts on the argument. We get k alpha a mu nu of k. This just stays sine k alpha x alpha. Be minus sign equals 0. And now, in order for this to be 0, what do we need? We need that this thing has to be 0, right? And this thing is, of course, nothing else than e squared minus p squared. So the fact that this has to be 0 tells us that gravitational waves travel with the speed of light. In vacuum. So only then are they a solution to this equation that we got from GR. Coming back maybe to the question I was asked earlier, for example, if there was a mass term, right, then we would have gotten a different result yet, right? So this is clearly an indication that we're dealing with massless degrees of freedom. So we can now be a bit more explicit in this to kind of have a feeling what a gravitational wave actually looks like. We can go to the transverse traceless gauge, and I'm just now going to specify that I want to put my z-axis in the direction of this k vector. And now, well, what this means is that if I now look at these conditions here, right, I want to construct something which is symmetric, which is traceless, and where essentially here these O mu components are 0. And also this here, right? This here tells me that I can have no components, since this I can Fourier transform, right? And this becomes a k, so I can, which I've put in z direction, so I can have no components in z direction. So I already know that when I want to look at this coefficient, this a mu nu of k, I know I will have a row of zeros here. So it's the first condition from the transverse traceless gauge. I will have a row of zeros here. And now, since I put the k in z direction, I will also have more zeros here. And now I can use the fact that it's traceless. So traceless tells me that the xx component has to be minus the yy component. Traceless. And this I will call h plus. So we have h plus here, minus h plus here. Now I know that it's symmetric, so I know that a xy is a yx. And this I will call h cross. So we have h cross here and h cross here. Right. So now you can put that essentially back in here, and you now have really an explicit idea of what your gravitational wave looks like in some sense in this particular gauge. So it's something which oscillates. It has these 2 degrees of freedom, and they are arranged in a matrix in this way. So we already here from this we see we're dealing with a wave in the sense that we found something which has a sine function. We found that the velocity is the speed of light. we see again, I mean, we derived it beforehand on just counting on just the argument of kind of how many degrees of freedom we started with and how many degrees of freedom we removed. But here we see now very explicitly that we only have 2 degrees of freedom left. And we also see that it is transverse, meaning that the directions parallel to the z-axis here are 0. So now we have this gravitational wave. So this is essentially what there is to say in some sense about a gravitational wave propagating purely in vacuum. Now I want to know what is the effect of such a gravitational wave on test masses. So we want to look at the effect of this gravitational wave on test masses, which are located, one of them at x mu and the other one at x mu plus xi mu. And now I'm going to cheat again. And I'm going to cheat because, okay, the result is important, but kind of the duration of this is not so relevant for the rest of the lecture. So I want to not waste your time writing all these indices. So what we want to know is how these test particles move when a gravitational wave comes along. So for that, we start with the geodesic equation. So the geodesic equation describes essentially how a point particle moves in terms of its proper time tau. And that is essentially determined by the curvature of the metric. So this is the description of a free falling particle. Now, what we're going to do is we remember that we computed the Christoffel symbols beforehand, right? The first order in h mu nu. So once we have the geodesic equation, we can essentially plug in our expression for the Christoffel symbols, and then we can also see how these test particles move in a curved metric or in a flat metric in the presence of gravitational waves. And what I'm actually interested in is not really how one particular test particle moves, but what I want to know is kind of what is the relative motion of these two particles, right? Because they will be two free falling particles, but now the gravitational wave comes and these two particles will move one with respect to the other in some way. And I would like to understand how does that motion work. And for that, I need what is called the geodesic deviation equation. So essentially, I have this equation, then I have the same equation again for this other particle. Then I subtract the two equations, and then I get an equation for this distance zeta mu between the two particles. And here we just see we have essentially an expansion in zeta. We go to first order in this zeta parameter, and so we have the Christoffel symbol again. We have something which looks like this term up here, and then we have one term here which includes this deviation parameter. We can now approximate that we want to be in the non-relativistic limit, which means that the derivative of the particle position with respect to proper time is small, essentially compared to the speed of light. And we can use that in one point, for example, in x mu, we can make the metric locally flat, which means that the Christoffel symbol is 0. We can, however, not do that globally, right? So if we do it at the point x mu, we cannot do it at the point x mu plus xi mu. We can do it at one point. And then if you use these approximations, you plug them back in here, you have to work for a little bit, and then you get this equation here. And then when you evaluate here the Riemann tensor, you finally, well, okay, let's start here. So this equation here again relates the second derivative of this xi, right, which was the distance between the two test particles with itself via the Riemann tensor, right? The Riemann tensor is the thing that knows now about the curved background, which knows about the gravitational wave. So we can now evaluate the Riemann tensor to first order in h using the expression I showed you on the very first page. And we can now make our life a bit easier because we've understood all these stories about degrees of freedom. So since we can already go into transverse traceless gauge and compute, because in this equation has to be gauge invariant, right? It's a physical quantity. So we can make our life easier and compute this object also kind of in the TT gauge. And then this is the final equation. So this tells us essentially how the motion of the particle is influenced by the presence of the gravitational waves. And the reason you have the two time derivatives here, right, is that the Riemann tensor came from the Christoffel symbol, and the Christoffel symbol had all these derivatives acting on the metric. So now we can actually solve this equation. So for example, let us consider the case where this H plus is non-zero and H cross is 0, just for simplicity, just to kind of study just one degree of freedom at a time. And this will, at the end of the day, be what is called the plus polarization. So the ansatz here is I'm going to introduce A and B now. A and B are just X and Y because I don't want to drag along all these zeros from above. So this is just H plus times sine. Again, we can write this a bit simpler. It's just sine omega t. And then we have just essentially the inner block of this big matrix, because the zeros I don't have to drag along. And this is so this was the H plus component, right? And it was a traceless, and hence it was 1 and minus 1. And now we have our two test masses, right? And I want to put one test mass. I want to, or the difference between the two test masses is x0 plus delta x, where this is the thing which can vary with time, and then this is y0 plus delta y of t. So essentially, I have a test mass, or I have a deviation of my test masses x0 and y0, and I want to kind of now see how these are moving, and the moving will be encountered in this accounted for in this delta x and delta y. So now I just plug all of this into this equation here. So then we get, let's look at the x component first. So then we get delta x double dot on the left-hand side. Now we have to take two derivatives of this guy. And so this will give a minus sign. Then we have this 1/2 here, so minus 1/2. And then we just get the function back. From the two derivatives, we get a w squared sine omega t. And now I'm interested in small deviations, right? So delta x should always be much smaller than x, so we can actually drop the delta x part. We can do the same for the y component. The difference for the y component is that you have a different minus sign here. So you will get, I forgot the h plus, it should be an h plus. So we get exactly the same here, just that instead of x, we get y, and we don't get the minus sign. So what does this mean? This means if let's just draw a picture. This means, let's say we have a coordinate plane, x and y. And let's say I have some test masses sitting at some points in this plane. Now let's consider first a case where the phase here is, so we're in some phase where the sinus is positive, right? At some time where sine omega t is larger than 0. Then we see that things that are that with respect to the y direction, so things that essentially, yeah, things with the y direction, things you have, like the sign of this is opposite with respect to the sign of this, right? Which means you can have, for example, a motion. Am I drawing this in the right way now? Yes, so here we have just an x coordinate, so this will go, and no y coordinate, so these will move like this. And these guys will move in the opposite direction. Yeah. like this, right? So if you have a positive y, the delta y will be positive. If you have a negative y, the delta y will be negative, and it's the opposite way around for the x component, right? So if you started, hypothetically, you started, say, not just with 4 points, but you started with a circle of points, then essentially in this phase of your oscillation, your circle will be deformed into an ellipse of this type. And now if you go to the other half of the phase, right, if you go to sine omega t smaller 0, then everything happens just in the opposite direction. So essentially you get deformed like this. Right, so then this is what I'm drawing here, and this is now you understand why I'm calling this plus polarization the whole time, right? So this is with some fantasy, you can see now a plus in this plane. So what is happening is you imagine you have a circle of gravitational waves, and as your gravitational wave, the gravitational wave is coming along the z-axis, right? So the gravitational wave is essentially coming at us, right, from behind the plane. And now all the particles on this surface, all these particles on this plane, they now start to oscillate in such a way that the ellipse always kind of deforms first in one direction, then deforms in the other direction. However, such that the surface inside will always be the same, because the surface is a scalar, and we're really just looking at tensor polarizations. Let me just briefly draw the second polarization, and then we can do. Then we have plenty of time for questions. So this is kind of what is referred to as the plus polarization, right? And then you can also do the cross polarization. So to do that, you consider the case where H plus is 0, H cross is non-zero, so the opposite case. And you go through the exact same steps, right? Just that now you have the off-diagonal elements instead, the symmetric off-diagonal elements. And then what you will find is maybe a good exercise to do to kind of convince yourself that you're following this. So we have the xy plane. And now essentially what happens if we start with our circle, it will be deformed in the one phase of the oscillation will be kind of be deformed into an ellipse like this. And in the second phase, it will be deformed into an ellipse of this type, right? And this is precisely why we call it the cross polarization. Okay, yes, there's a question. Gotham.
Yeah, so is this sort of similar to what happens when a gravitational wave passes through a planetary object?
So this applies to any test masses that you could consider.
Okay, so like this difference in sort of stretching and compression is sort of what we measure in like laser interferometry.
Exactly.
Okay.
So what you would so if you would build a gravitational wave detector, right? Then you would, for example, let's say we want to measure this gravitational wave, right? We would build an interferometer, ideally, which is aligned precisely in this way, right? And we measure, the interferometer measures this distance, right, with respect to this distance. That is the measurement that the interferometer makes. And now, as the gravitational wave comes through, right, this distance is now shortened, right, and this distance is stretched, and that's precisely what the interferometer will measure.
Okay, thank you.
There was, by the way, historically there was a long debate if this is actually something that could be conceptually measured, because kind of the question is, well, but what if? So you're trying to measure a distance, right? But you're actually perturbing the metric. So in some sense, you're changing the distance, but you're also changing the ruler with which you're measuring the distance, right? And hence you have to be really, and this is essentially where all this discussion about the gauge freedom and what is actually physical and what are gauge artifacts, where this enters. You have to be kind of very careful of what you're doing to really make sure that you actually are convinced yourself that this is really something physical that you can conceptually measure. And people were essentially, I mean, the computation was there, right? But people were still a bit confused. And the reason then why people, the argument which apparently in the end really convinced people that it was a physical effect was kind of the argument which is called the sticky bead argument, that you imagine you have an infinite rod and you have a bead which is on this rod and can move up and down, but the rod is sticky, so that there's some friction when the bead moves. But since now the rod is infinite, right, there's no question of does the ruler change, does the ruler not change, right? The gravitational wave would now move this bead up and down the sticky rod, and then the friction force would be something, or the heat from the friction would be something which you can objectively measure independent of the question. I mean, in theory, right, which you can measure independent of the fact if kind of now the rod is stretched or the rod is not stretched. So this, yeah, apparently this is historically this was one of the arguments that convinced people that this was real. But now that we are kind of now that there's consensus on this, I think now this kind of this picture that you're just kind of stretching one arm with respect to the other is perfectly fine and accurate. So in conclusion, what we learned from this discussion of these plane waves, we learned that we have, just to summarize, we learned that we have 2 degrees of freedom. So when we linearize general relativity, we get 2 degrees of freedom we can describe, which corresponds to 2 linearly independent solutions. Which are plus and cross. And now, by the way, I also think I understand better. Someone was asking before, and if the 10 degrees of freedom were really linearly independent. And yeah, I mean, in fact, I think my answer was not quite correct, right? I mean, this is in the end the correct answer, right? Once you take into account all the gauge degrees of freedom and so on, right? Then in the end, you really just have 2 degrees of freedom that you can discuss. They are propagating transverse waves. Which deform a 2-dimensional plane. So this is different than electromagnetism, right? In electromagnetism, you also have transverse waves, but there, the entire thing, like here you really 3 dimensions, right? 1 dimension is the one where the gravitational wave is moving, and then the plane orthogonal to this is deformed. Whereas for an electromagnetic wave, of course, you can draw the entire thing in 1 dimension less, right? Because essentially the formation is only in 1 dimension, not in 2 dimensions. This is precisely why essentially the photon is a vector particle, right? The 1-dimensional, a spin 1 particle, and here we have a spin 2 particle. Yeah, so it's important to note that this is a spin 2 particle that we're discussing, meaning, or in other words, this is a tensor. And it's important really to stress this is an inherent prediction of general relativity. So there's no quantum gravity involved, no BSM physics. This is just something which kind of has to be there if general relativity is correct. And maybe one more note. So here we've talked about the plus and the cross basis. Sometimes people also talk about the left and the right basis. So HLR. And this is just in case you ever come across this. These are related. This is again very similar to electromagnetism. These are related to these 2 guys by in this way, plus minus I H cross. So it's just 2 different linear combinations, but I mean, at the end of the day, you've 2 degrees of freedom that you want to describe. Okay, are there any more questions? I have one last polling question, which we can do in parallel. Yes, Manuel.
So, thank you for taking my question. Can you elaborate a little bit more about this stretching of the metric, and that it is actually a physical effect and not that we can measure?
Right. So you
because
have
my first equation would be like it would be not measurable.
Right, and I can say that that you're in good company, right? That this was actually a long discussion. So in Majora's textbook, right? So in this textbook here, at the beginning, here this first one, there's actually 2 chapters dealing just with this question. And essentially, there are two frames where it makes sense to discuss things. One is kind of what is called the free-falling frame. So in the free-falling frame, kind of your test masses are free-falling, right? And then you kind of look at the effect of the gravitational wave on the trajectories. And you can, this is essentially where this argument with the gravitational deviation equation or the geodesic deviation equation comes from. So you essentially really asking kind of, do trajectories deviate from each other? So that's one frame to look at. And the other frame to look at is what is referred to the proper detector frame, where the detector is not, because the detector is not a free-falling object, right? It's fixed to Earth. It's not on a free-falling trajectory. And in both the cases, you can, the danger arises when you mix essentially two situations, right? Then you can confuse yourself about what is physical and what is not physical. But if you kind of carefully stick to one frame or to the other frame, then you can convince yourself in both frames that it is really a physical effect. And essentially in one frame, and now don't ask me which one, in one frame, essentially you can understand the gravitational wave as really a change in length scales. This is, to me, a bit more the intuitive understanding, and this is in the detector frame, right? Because this is really like how an interferometer works. And in the other frame, in the free-falling frame, you instead have to think of it essentially as a shift in time instead of in space. So essentially, the travel time of the travel time of the objects changes. So the gravitational wave perturbs the proper time of the moving objects. And again, this is a measurable physical effect. But
Okay.
yeah, you have to. It is quite easy to, But this all kind of boils down to doing kind of the gauge fixing in a proper way. And for example, this transverse traceless gauge, which I use today and which I will use in most of the lectures, and which actually most of the people use all the time, and it is really a gauge which only works in vacuum, right? So it's actually not a gauge that you can use really when talking about detectors. But people do it anyway, and most of the time it's fine. So it's one of these cases where you can do a really good proper computation. Once you know the result, you can kind of do a shorter computation and reproduce the result. But I strongly encourage you to look into, it's in section 1 or 2. There's a long discussion on proper detector frame versus free-falling frame.
Okay, thank you very much.
All right, next is Ivan.
Yes, I wanted to ask a following question. In different lectures and different book, I heard the term harmonic gauge and harmonic coordinates, and I wanted to ask if they are related to the gauge which was used today.
Honestly, I don't know. I don't know what is the harmonic gauge.
Okay, I'm asking because the derivation looks very similar to a book which I'm reading, but they're using harmonic gauge. So I'm wondering if it's the same or if they're different. But I guess you don't know. Okay.
No, I don't know the harmonic gauge. I mean, I know that you can use different gauges, right? I mean, here we use Lorentz gauge, and it is obviously different choices. Very similar to the story in electromagnetism. You can also do something like Coulomb gauge and so on. Yeah, but not this specifically. I don't know.
Okay, thank you anyway.
So I encourage you to do the last poll question here because this is kind of telling me what was the speed of the lecture like, and this is crucial for what you will be facing tomorrow. So this is your chance to have influence. Any more questions? Adriana?
Sorry, Adriana.
Yeah, so I know that there is a lot of complexity and discussion on how to define the energy of a gravitational wave. So I'm thinking, when we write the linearized Einstein equation, how should I interpret this energy and momentum tensor? Just like only Newtonian matter in there?
Okay, so we'll touch a bit on that tomorrow. So as long as, okay, so essentially what we did today, right, is that we took a flat space-time and we perturbed it with a gravitational wave, right? And in that case, it is kind of clear more or less clear what is a gravitational wave. The complication arises when you have curved space-time. And in fact, as soon as we have a non-zero energy momentum tensor here on the right-hand side, it essentially means we have curved space-time. But when you have curved space-time, this means that your space-time is space and time dependent, or at the very least, it is space dependent. So then the question becomes, how do you actually separate the background part from the perturbation part, right? Because if the background part now also has a space dependence, then how do I know what to put in the background and what to put in the perturbation? And that is kind of where the difficulties come from. And we will talk about that a bit tomorrow, but I mean, I can tell you that the overall strategy is that you need a separation of scales. So you need to essentially say, I can do some sort of averaging procedure at some scale, and I need essentially that the background is say homogeneous at these scales, and the gravitational wave is not, right? So if I want to, for example, measure a gravitational wave with LIGO, then we use the fact that, of course, LIGO is not in vacuum, right? And so there is the gravitational potential of the Earth and all sorts of stuff. So what we used is the fact is that the gravitational waves that we see with LIGO oscillate at a frequency of Hertz, but the gravitational wave backgrounds that we have from whatever, you know, the Earth and whatnot, they move only very, very, very slowly. So if we do a time averaging procedure, which on a time scale which is much longer than the oscillation time of the gravitational wave, but much slower than the oscillation of the gravitational wave, but much faster than anything where the background would change, then we can in this way separate the gravitational wave from the background. But in fact, it doesn't make sense. Like in curved space-time, so in vacuum everything is easy. In curved space-time, it doesn't make sense to talk about a gravitational wave without kind of specifying how you have even defined what is your background.
Thank you. And so related to this, whatever is sourcing the gravitational wave, is it contained in the like classical? I don't know how to express.
So sorry, say that again.
So the gravitational wave is sourced by something. So I'm wondering if this something is also problematic or if this is just in the stress energy tensor.
This is just in the stress energy tensor. Yeah. Exactly. So in practice, how this will work is that you have so some event which is localized in space or time that creates a bunch of gravitational waves, and then they just propagate through the vacuum, and we can describe them just fine, right? And then when we detect them, we have to again be a bit careful. Yeah, and we'll talk about in the last lecture. We'll talk about sources. I mean, the most obvious source is essentially the one that the detection at LIGO, or many detections as LIGO has already made, right? From two black holes colliding with each other, right? That kind of disturbs the metric so much that kind of we get a radiating signal. This is the gravitational waves that LIGO has measured. And yeah, there you would essentially say, okay, there was one event in space-time, this is the merging of the gravitational waves that generated these gravitational waves. That's in fact a very complicated process to model that really to high accuracy. But then once they're kind of propagating in vacuum, they are very easy to describe. I should maybe also mention, I probably should have said this at the very beginning to catch your attention. So the reason why gravitational waves are such a unique way to probe particle physics and to probe the early universe is that when we use photons to probe the cosmic history, we can always only probe back until the decoupling of the cosmic microwave background. because at early times the universe was like there was a plasma, it was charged particles, and light didn't propagate freely. So it's very, very hard to probe any times before the CMB decoupling. But gravitational waves really don't care at all if the particles are charged or not charged, right? Because they don't know about charge, they just know about masses. So gravitational waves, in principle, can probe the entire cosmic history up to cosmic inflation, and in principle retain the information. And if we can detect them, right, then we can decode all this information. Then the problem is, of course, that the gravitational wave, it doesn't care about all the plasma in the early universe. It also doesn't care a lot about architecture, right? They tend to just they're so weakly coupled that they're extremely difficult to detect. But that is kind of that is the underlying reason why this is potentially a very promising tool for particle physics. I see another question by Max.
Yep.
Yeah, hi. So I have a question related to that, what you just said. So you said that in this propagation region, one usually assumes that there's just vacuum, and therefore we can really know what gravitational waves are. So, but are there some situations which people are already thinking about, or really are physical, where maybe this approximation could be problematic? Yeah.
Well, yeah. So I mean, gravitational waves interact extremely weakly with matter and stuff, right? So and the universe is pretty empty, right? So for most of the time, it's really fine. I mean, the gravitational wave, I mean, sure. I mean, if you have whatever, you know, if you have some massive objects in the path of the gravitational wave, then the gravitational wave will be lensed just in the same way that light is lensed, right? But this is something we understand, right? Essentially, this just kind of means that the trajectory of the gravitational wave changes. And this is in fact something that people have looked at. There was, for example, at some point there was the case that LIGO had measured two black hole merger events, which were kind of close together in time and looked maybe somewhat similar. And people were speculating if maybe one event was the lensed image of the other event, right? So both one event, but then kind of two trajectories around some very massive object, then both kind of being detected at Earth. So these are the type of things that people have looked at. But apart from that, the gravitational wave doesn't care much if there's whatever, you know, if there's a cloud of hydrogen or something in the way, it just doesn't care. That what makes it so powerful to probe the very early universe.
So therefore you're saying that basically the only region which could be problematic would be if the region would be exactly the one which also produces gravitational waves, like some binary system closely before merger or something like that.
Right. Because there also we have the problem that the perturbation is not small, right? Because here I'm always working in the linearized theory, right? So I'm always saying that H has to be very much smaller than kind of the metric itself. And now if you're very close to a black hole, that is no longer the case, right? And so these black holes are merging, then you have to deal with strong gravity, and that is difficult. And then you need to do that properly, you need numerical simulations.
Okay, thank you very much.
I see no more questions. There was a question in the chat. Francesco,
yeah.
You can read by yourself, or should I read? So Francesco asked whether the reference that you gave by Maggiore contains explanation of the SVT decomposition.
Yeah, so the Maggiore textbook contains the discussion about how you do the individual gauge fixing steps, right? To then arrive at the 2 degrees of freedom. So she talks about Coulomb gauge and these things, and the transverse traceless gauge. Now this story here is kind of the very general picture of cosmology. It goes under the name of cosmological perturbation theory, and I honestly haven't found a perfect reference, but a good place to start reading about this would be the Tasi lectures by Daniel Baumann. So Daniel Baumann, I think there's 2 N's, there may not be, I'm not sure. Tazi lectures. And here's one on inflation and one on, I don't know, called cosmology or something like that. And they both in the appendix of these lectures. I found those useful.
All right.
And I see another question.
In the chat, no, by Antonio.
Yeah. Could you tell us a little bit about gravitational waves as a test for particle production during reheating? Can I help us to understand if there has been a preheating or not? Yeah, that's a very good question, and we'll come a little bit to it in the third lecture. I can give you a spoiler, and that is that. So in principle, yes. So preheating is a very in order to source a gravitational wave, right? What you need is this energy momentum tensor, and in particular, since we need to solve a tensor perturbation, we need an energy momentum tensor which actually has a tensor contribution, which essentially means we need an anisotropic energy momentum tensor. So typically, if you have some very violent process which is not symmetric, symmetric meaning there's no radial or spherical symmetry, then you generically source gravitational waves, and the more violent or the more energetic your process is, the more gravitational waves you get. So preheating is very violent, right? It's very high energies. It's not at all symmetric, right? You may have bubbles which collide and all sorts of things going on. So it's a strong source of gravitational waves. However, the problem is that preheating happens typically at like a very high, very early in cosmic history, which means that the gravitational waves get diluted a lot until they reach us. And also kind of the length scale of the gravitational wave involved depends on essentially on the typical size of the process. And then of course you have the redshift to today. But if you kind of look at whatever, the typical mass scale of a preheating particle, of an inflaton particle, this is a very high mass scale, which means it's a very, very small length scale, which means it translates to extremely high frequencies today. So the highest frequency that we can probe with LIGO is something like kilohertz or so. And in order to really probe like broad classes of preheating models, you would need to be able to do megahertz or gigahertz or something. And there's several ideas out there, but there's no clear path forward on how to detect gravitational waves at those frequencies.
Okay, he says great. Next question by Antonio.
Maybe this was the
Again,
same,
the same one.
Yeah.
Yeah. So yeah. Okay. So then Artemis, please go ahead.
Yeah. Can you hear me?
Yes.
Yeah.
Okay. I was just wondering, you mentioned that what we did today works for a massless graviton, so massless gravity. What would change if we had a massive particle?
Yeah, so I'm not an expert on this, but I mean, if we look at just kind of the final properties, right? So one thing that would change, it would no longer propagate at the speed of light, right? But it would kind of propagate at whatever speed is dictated by its mass. We would also have more than 2 degrees of freedom. And you can kind of understand that by the analogy with electromagnetism, right? So the massless photon just has 2 degrees of freedom, the 2 transverse degrees of freedom. But if we give it a mass, we in addition also have the longitudinal degree of freedom. And the same is true for gravity. So in models where you make the graviton or you add a mass term to your gravitational waves, then you don't only have these 2 degrees of freedom, the plus and the cross, but you have additional longitudinal modes and additional scalar modes. And in fact, one of the things that LIGO has already done is they have checked, for example, if they have in their data, right? They've seen these modes, right, from the black hole mergers, and they have, for example, checked if they have. And this is what you expect, right, from GR, but they have also checked in their data if they have any indication of detecting other modes. But so far they have not, right? Otherwise we would have heard.
Right. My question was more like, I understand, of course, it's going to be a difference at the end, like the solution we get will be different. but I'm not sure I see, well, I haven't seen actually how it would work. What would be the equation that would start it from? Because we started from linearizing Einstein's equation, and
Right, so
we have no particles in there. So like, I guess we would have to do a QFT approach or something like that to have like,
well,
because we have no particle. Like we end up with a box operator without a mass, but like,
well, we would have to modify GR, right? Because
okay,
I mean,
right.
in GR, it's a prediction that the gravitational waves are massless, right? So what we would need to do is we would need to not, so this, our starting point was Einstein equation, right? So general relativity. If we want to somehow arrive at a theory which has massive gravitational waves, we need to start with a different theory. So essentially we need to modify, in some sense we need to, well, I don't even know if it's entirely correct to say we need to modify the left-hand side, but we need to modify this equation. We need to have some more complicated form of this equation, which allows for extra degrees of freedom. So really the starting point changes, right? And then if this changes, then of course, this equation changes, right? And then of course, this equation changes, right? And you will no longer just have box H on the left-hand side, but you will have something more complicated.
Okay, thank you.
Do you have more material to cover today, or
no, I was done.
Okay.
I took it seriously that you said 2 times 35 minutes.
Okay. 45, I said.
Well, it was, yeah, it's
fine.
It's fine.
Perfect.
We could, yeah, no, it's fine. We could start with the next. No, I think this is a good point to stop.
Perfect. So let's stop the recording. Okay. Okay, great. And there were many questions, but there is more time for more. So now the recording is not on, so don't be afraid to ask any question.